Right now I'm measuring the static pressure. Why do we measure static pressure? Because we need to know how much airflow is going through here. When we design a system, we design a system for 0.5 static pressure. If we're above that, that means there's a restriction and it's harder to get airflow across the coil. Airflow is key to efficiency of equipment. If we have too much restriction, we don't have efficient equipment. So when I look at this, I have a return and I have a supply. So what this is measuring is external static pressure. That external is all this ductwork, all the things that are beyond the system. So we're isolating that, and if it's higher than 0.5, then it's a restriction. It's a resistance factor. If it's lower, that's good. That means we don't have much of a restriction for all the things that are external to this, to the heating and cooling system, or to the furnace and the air conditioner. So when I look at this, I actually have a 0.46, which is good, because in 0.46, we're lower than the design of 0.5. So there's a chart for this manufacturer which will tell me how much airflow is going across that coil based on this number. So I have to use the manufacturer's data to look that up though. So right now this is good. Now we know there's another problem with this system, and that problem right now is we're creating a restriction that is unnecessary. That restriction is this filter. So if I pull this filter out, we can hear immediately that the air is increasing and that it got louder. I'm very close to design external static pressure with the system, so it should be getting maximum airflow. So I'm going to test that with another device called a true flow plate, and that's going to measure exactly how many cubic feet a minute of air we are going across the system. This is a true flow air plate. What we're going to do is we're going to put this inside the furnace where the filter slot normally goes, and we're going to actually measure how much air is moving through the system. And that'll give us an accurate determination about design, 1,200 square feet a minute, and actual, and we'll figure it out. Now that we tested the system, we know that we need 1,200 CFM, and we have 1,135. Not horrible. We're still a little bit low, but that's not horrible. It's not as bad as we expected. Right now I'm going to get a baseline of how much air is coming out of each of the vents into this room. This is a bolometer, and what the bolometer does is it measures the amount of air that comes out of that vent. And based on a load calculation for manual J, we should know how much air this room is supposed to get. So we have multiple vents in this room. We have this one, another one over there, one in the bathroom, and one in the closet. So when we add all that up, that should tell us how much air we need for the room to satisfy the cooling call. So what I'm going to do now is actually add these numbers up, measure these numbers, add them all up, and see if we have the adequate amount of air to cool the room by design. So a lot of people put things together and they always say, I can make it work. Great, I'm glad you made it work. But we want to make it perform. And there's some things that they've obviously done wrong here that prevent the performance of the room. That's why we have hot and cold rooms. So before we start balancing anything, we want to see the performance of where the baseline is and where it starts. Like one of the things that I noticed right away when you look up at this duct is you can tell that we have the wrong duct grill for the room, because this is a diffuser, and what it's doing is it's diffusing the air to make it go in all different directions and not any place that we want it to go. The ideal situation is if we had a single set of fins that would force the air down toward the floor about 14 feet away. And the reason that we want to do that is we want the air to come out with some velocity and then mix in the room for total comfort. This way, all the air is not stratified with the hot air on the top, the cool air on the bottom. We're going to be at an even temperature throughout the room. So by putting this in, you're defeating the purpose and you're wasting all the velocity that would come out of this duct. So if we put this device up there and we measure it, we can see how much air is coming in from this particular duct. And then we're going to see if we have good duct design and if we have enough air that we're supposed to have.
So right now we have, looks like 109, 110, 114. All right. So when we write all this down, we're going to add it up and see what we're supposed to have. And then we're going to match that to our design. Because if people don't do a manual J, you have no idea where you're supposed to be. And to me, that's just stupid. So what we want to do is figure out where we're supposed to be, check the baseline of what we're actually getting, and then do things to improve that situation to make it closer to the correct design. 99% of my competitors don't do a manual J calculation, so they have no idea the target they're shooting for. How can you hit a target that you don't know you have? Which is why when people say to you, oh, I can make it work. Great, you can make it work, but does it work well? Because it's about our comfort. That's what's important. So it's not about just making it work. It's making it perform, making it satisfy the homeowner, making people who are living in the space enjoy living in the space, not suffering because of the poor design. And we're going to take you into another room in a moment, and we're going to show you what immediately we know why we have poor design. So let's go over there and I'll show you the worst thing. I'm going to measure this room now, and I'm going to see how much air is coming out of the duct. This is the most uncomfortable room in the building, and we should have a significant enough air coming out of this duct. And I actually don't see a significant amount of air coming out of this duct, and I pretty much know why. So we have 35, 36 CFMs for this room. We actually measured some closets that have more air coming in than this whole room. So that's 35 coming in. We also have a bathroom over here, which has another duct in it, which is part of the return cycle for this room. And if we measure this, we're going to find out that we have 15 cubic feet a minute of air coming in. So 15 and 35 is 50. So 50 for the bathroom and the whole room coming in. Now what we can also do with this device is measure the return air going back. So if we look at that, I hit the switch, and now I'm going to measure how much return air is coming back. So this is supplying the room, and this is taking the air out of the room. So let's measure this. And oh boy, that's not good. That's getting worse. That's even worse. All right, so what we have now is 159. Do we cross to 160? There it is. 159, 160. So what that means is that we have 160 going back and 50 coming in. That means we have 150 cubic feet a minute of air leaving more than we have coming in conditioned air from the system. So what that's telling me is that we have leakage from someplace other than the duct system. Because if this is pulling more air back, then that means, and we're not delivering as much air to the room, then that means we have leakage from someplace else. And if we look around, we see that we have these recessed lights in the ceiling. Those are directly connected to the attic. That's 130-degree attic space. So therefore, we're going to pull 130-degree air back in from those can lights so that we can let it exit through this return. And then we're only putting 50 into the entire room and bathroom, which means that we have a deficit. This room, by running the air conditioning, is making the room worse because we're taking more air away. And where we're taking that air away is from outside the conditioned space. That means if we pull it in through the walls, the windows, the floors, underneath the baseboard, then that means we're pulling it in at 85 degrees in the summertime. If we're pulling it from the attic, that means we're pulling it in at 130 degrees. So we're trying to cool and condition a room that is never going to work because we're pulling more air in from outside than we're actually conditioning the air within the space. So that's why this is a problem room. And I know what the problem is because I've seen the ducts up in the attic, and I'll explain that when we get up there. But this problem room needs to be addressed so that we have at least a balance point where we're putting as much air into the room from the conditioned air conditioner as we are taking it away. Because right now, honestly, I feel hot, sticky, and humid standing here. And There's no reason that an air-conditioned room should be hot, sticky, and humid. It's just not, because air conditioning pulls moisture out of the air. So, that's our problem. But we're going to get this fixed. We're going to balance it. We can't balance it until we know the numbers. That's why we're measuring this today. And we can't know what the target we're going to hit unless we do a manual J load calculation on a room by room basis. And like I said, 99% of my competitors, they're not doing this. They're looking and going, yup, I can make it work. Great, you can make it work, but it's not working well. Right now it's working, but it's not working well because we're uncomfortable. We're unhappy. The homeowner's unhappy. We're hot, we're sticky, and we're not cool. So it works, but it's not working well. It needs to perform. And that's what we're here to do. Make it perform. So when we're done, they're going to be a much happier place than they are right now.